My name is Rick Blum, and it's my pleasure to talk to you today about our project on GPS spoofing attack detection. You can see myself and my collaborators are all from Lehigh University, and we're part of the Seed Center. Phaser measurement units generate high-frequency, time-stamped electrical grid measurements, and they're used in fault analysis, enhanced state estimation, event analysis, stability analysis, system visualization, and many other applications as well. Now, these PMUs, phaser measurement units, generate timestamps using publicly known civil GPS signals that are not encrypted. And it turns out that devices that can generate counterfeit GPS signals are inexpensive to produce and easy to construct using existing integrated circuits. And these are called GPS spoofing attacks when the GPS unit receives one of these counterfeit GPS signals. The benefits of our technology are that it is able to quickly and accurately detect GPS spoofing. It can handle complex network topologies with multiple PMUs under attack, and it's very easy to deploy. It requires no change in infrastructure and no interruption of system operation. Now, our technology, in terms of commercialization, can be implemented at individual PMUs or control center or at data concentrators. So we have actually two methods, and in the first method, the technology can be implemented inside PMU concentrator boxes or in custom boxes in the control center. Method 2, the technology can there be implemented in the PMU units themselves. In terms of our approach for attack detection, again, we have two methods. Method 1 attempts to detect changes in the model of the power system grid that would occur if these GPS spoofing attacks were launched. So we basically characterize mathematically how these GPS spoofing attacks will change the model for the power system. In method 2, instead of looking at changes in the model for the power system, we're able to detect changes in the signal model of the measurements, right? So again, we've mathematically characterized what these GPS spoofing attacks do in terms of changing the signal model for the measurements. So in either case, we've devised a statistical hypothesis test to distinguish between two hypotheses. One is that there is no attack and the system continues to operate in unattacked mode, and the other one is that there was an attack. And we're using the well-developed theory of statistical hypothesis testing that is used in the electrical engineering departments in all schools under the heading of signal processing, right? So this is under signal processing. And if you want the details of what we're doing, we're using something called a generalized likelihood ratio test. Now, why is our approach better? Well, it turns out that the majority of existing methods to suppress these GPS spoofing attacks essentially focus on the signals that are communicated between these satellites and the GPS receivers. It turns out that none of these methods completely eliminate vulnerabilities, and it turns out that our solution can handle attacks not detected by these methods. So in fact, our methods can work together with these methods that look at the signals communicated between the satellites and the GPS receivers to give you better overall performance in halting these GPS spoofing attacks. Our methods, it turns out, focus on using our understanding of the characteristics of the power system, and in fact, any other methods that do something similar that we've compared to, our methods have significantly outperformed these other approaches. Now here's the summary of our project status. So for algorithms, the method 1, the algorithm has been completely developed. We have simulated this method 1 in MATLAB using very well accepted models for power systems in the power system community. Our testing continues. We're progressing from simulations to alpha and beta testing, and we expect to finish testing this year. Now, we're testing using all of the facilities available in the SEEDS project laboratories. So we're using whatever we can at Lehigh, at Florida International University, and also at Arkansas. So right now we're testing in the Smart Microgrid and Renewable Technology Research Laboratory at Lehigh University, which allows us to test our technology in a much more realistic environment and to perform real-time testing. And we hope also to include some real PMU hardware that's available at FIU and also to use what resources are available in Arkansas. What does this project need from industry? Well, we need PMU concentrator and PMU manufacturers to implement this technology in their products. And in summary, Method 2 will be completed with next year's funding, and we'll go through a similar round of testing and then with simulations and alpha beta testing to follow. In closing, if you want to learn more about this project, if you'd like to provide feedback, or if you'd like to discuss collaborations, please contact me at the email address shown. Thank you very much for your time. I hope that you enjoyed this presentation.